Hello, I'm John Dwyer, author of Multifactorials and Primes for Cryptography. This time we're going to be looking at Chapter 7, which is on Diophantine equations, and we'll be looking at a proof for Fermat's last theorem. So we'll look at the slides now. Okay. So this time we're looking at Diophantine equations. Obviously in cryptography, we're interested in solutions of equations with integer, prime numbers, particularly large ones, and Diophantine equations help us with that. So here's an example of a polynomial, x cubed minus 6x squared plus 11x minus 6, and you can see that we have three roots. Could have seen this by factorizing, and x minus 1, x minus 2, x minus 3 are all factors of that equation. So x equal 1, 2, 3 are solutions. Sometimes we get repeated solutions. Here's an equation, factorizes to x minus 1, x minus 2 squared. So we have three roots, x equal 1 and x equal 2 twice. Turns out all cubic equations have either one real root or three real roots, never two. Interesting property of any cubic equation with repeated roots is that the derivative must be 0. Elliptic curves are a particular example using polynomial equations. Y squared equals x cubed minus x. There's an interesting curve. And y squared equals x cubed minus x plus 1. Another interesting elliptic curve. Now Fermat's last theorem is usually expressed as a to the n equals b to the n plus c to the n, where n is an integer 3 or bigger. Turns out that integer triple solutions, a, b, c, for this equation cannot all be integer. Two of them can, but the other one can't. And we'll prove that in the next couple of slides. 7 steps to the matrix diagonalization proof. First of all, we construct, for a given n, a lower triangular matrix Cn, and all of the elements are differences of nth powers of numbers. For a given row A, we fill in the elements from right to left. Now it's important we go right to left. The size of the elements increases all the way to the end of the row. We divide into two parts. Those elements that we encounter which are less than the previously found integers to the power n, we show algebraically that none of these can be integers to the nth power. For those elements which are greater than the previously found integer, we show that none of these elements can be integers to the nth power. In fact, when we get right to the end of the row, the last element that we get is just one less than the next integer power. So none of the elements in Cn can possibly be integers to the power n. So we form a list, step 7, and the list contains all of the integers to the power n, and none of those can possibly appear in Cn. So here's step 1, the very first element, apart from the leading diagonal zeros, is 2 to the n minus 1 to the n. That's on row 2, and that will be equal to 7, obviously. On row 3, we get those elements. We start from the right and move to the left, and then proceed down the matrix. Now, along any given row, for a value of a, the number that we encounter less than the previously found integer, we assume that a minus x to the n is equal to c to the n, and see what values of x we get. Well, there's the equation for x, easily expressed, and there's the curve that we get for x. Notice that when we differentiate x, equation 7.3, we get a positive gradient. Interesting result. In fact, it turns out that the nth derivative of f is n factorial, which ties in nicely with chapter 2 on multifactorials in the book. So we find that x cannot possibly be an integer. It can't even be a rational number because x must be an irrational number to have a positive gradient everywhere in the interval 0a. So we know the derivative of f is non-zero, so we can use Newton-Raphson. Start with an initial guess for the value of x and then iterate. And there's an example with a equal to 10, m equal 1, and n equal to 3, C3. And that correctly gives the element on that particular row and column. As we proceed along the row, right to left, we can see that no values can possibly be an integer to the nth power. The values that we do add to a dynamic list are the last elements in each row plus 1. And those are the integers to the power n. And there we are. Example, C3, n equal to 3. They are the differences between powers, third powers, I cubed minus j cubed. Let's look at the 10th row. The first element that we encounter is 271. This is less than 729, the previously found integer cubed. Now we've shown algebraically that the value of x that corresponds to this, which is irrational, must give rise to an a to the a minus x to the power n, which cannot possibly be an integer cube. Similarly for 488 and for 657, once we get past the last value of an integer cubed, 784, 875, 936, we see that these numbers cannot possibly be integers cubed. The next integer cube that we get, as we get to the end of the row, 999, we add 1 to that, and that's the next integer cubed. C4, pick up random another row. We'll start with that one, which is, I think, the 9th row. 2465 is clearly less than 4096, the previously found integer to the power 4. There's only one of those, but we've shown algebraically that the corresponding x and the corresponding a minus x cannot possibly give rise to an integer to the power 4. Get to the end of the row, 6560, add 1 to that, and that's the next integer cubed. Last one, C5, where n equals to 5. We have two elements that are less than the previously found integer to the power 5. 16105. Was that number? So in this case, we have 87781, 148832, and they are both less than that previously found integer to the power 5. None of them, neither of them, can be integers to the power 5. Then as we proceed through the green numbers along that row, we end up with 248831, add 1 to that. That gives us the next integer cubed. Notice in these matrices, none of the elements, which are differences of powers of n, can possibly be themselves integers to the power n. In chapter 7, we'll look at various numbers which relate to this work: Cuban, Quartan, Quintan, sexton, pentan, until we get to the general Polyan numbers, which are the numbers that fill the lower triangular matrices that we've looked at for Fermat's theorem. The rest of the chapter, we'll look at applications of Diophantine equations in cryptography. In this case, we'll look at them geometrically, and we'll look at theta functions, elliptic curves, and infinite dimensional lattices, which takes us on to the next step in Diophantine geometry. If you have any questions about this material or chapters in the book, email me at the university, john.dwyer@roehampton.ac.uk, and thanks for listening. Bye.